All right, hey guys, what's going on? So again, if you like this kind of content, please remember to subscribe to this channel. Today we're going to be talking about the Hamiltonian again, but we're sort of thinking about this in terms of sort of like now a spatial Hamiltonian, because we really only worked with the temporal part of our Klein-Gordon equation. Now we're going to be working with our spatial part. We're going to be using the same prescription. We're just going to be achieving something different in this case. So I'm going to call this the spatial Hamiltonian, if you will. Okay, it's not really a technical term that's used in the book. But anyways, let's get right into this. But before I get into the whiteboard, I want to mention just a few things. The first is that I'm going to now focus on this book until we get to the end, right? So this is No Nonsense Quantum Field Theory by Jacob Schwittenberg, okay? We're gonna get to the end of this now. We're gonna speed up our process, maybe 2 or 3 videos a week, hopefully 3. And that is thing number 1 that I wanna take care of. Thing number 2 that I wanna take care of is that this channel is now hopefully going to become bigger. A few things are sort of on their way in terms of making the channel more conducive to hopefully what you guys would want to see, right? So I have animations coming on their way, and I also intend to make these videos a little bit more animated, if you will, right? So we're also going to have the whiteboard. With all that being said though, I really aim for this channel to go full force forward, and I hope to see you guys in the future. I love how this channel is starting to blow up. It's not really blowing up fast, but it's increasing, and I am very happy with the turnout so far. So let's get right into the material. All right, so we're talking about the spatial Hamiltonian today. The spatial Hamiltonian, this isn't really a term you see, right? I sort of just made this term up because we're following the same prescription as we did when we achieved the Hamiltonian in a previous video. We used that Hamiltonian to understand that we have something called a ground state energy. This was a video entitled Something from Nothing. This is something that Lawrence Krauss has talked about before, and where you have, if you start off with the Klein-Gordon Hamiltonian, you are able to sort of understand or realize that at the ground state where there's no particles, there's still energy. A very, very weird thing to think about. In the presence of no mass, there's still energy. But that was in terms of talking about energy. Now we want to sort of talk about momentum, because momentum is sort of the spatial correlate of energy, as we've seen in 4 vectors from a long, long time ago. So let's get right into this. We want to recall a few things. So one of the things we want to recall is this right here. We obtained this from quite a few lectures back. I believe this was in chapter 3 or chapter 4, where we had this thing called the energy momentum tensor, and it could be achieved by the Lagrangian through this. As long as we had the Lagrangian, as long as we had the solution to our Lagrangian, where we were able to derive this energy momentum tensor, right? The energy momentum tensor is a symmetric object under space-time symmetries, or is a symmetric object under space-time transformations, as we've seen before. If you don't understand what that means, I would refer you back to understanding what the difference was between coordinate transformations and space-time transformations. Again, that was chapter 3, I think. Let's go into, so that's where we came up with this idea, right? So this thing was the thing that that remained invariant under those types of transformations, right? So we've talked about this already. We've talked about this, and we've talked about this right here, right? So the energy of a system is given by an integral over some volume of space of this temporal part of the tensor, of the energy momentum tensor. we also came up with this, right? So the correlate to energy is momentum. This, or you can think of momentum as the spatial part of energy, or energy as the temporal part of momentum. That's again encapsulated in what the energy of momentum 4 vector is like, and so forth. But anyways, here's our momentum, and our momentum is achieved by, again, taking that integral over some volume of space of the temporal part of this tensor, this energy momentum tensor. The way we say it's the temporal part is by putting an I here, right? So the I runs over 1, 2, and 3, with the 1 being the x direction, 2 being the y direction, and 3 being the z direction. Again, I'm not going to go too deep into this because we've done it before. And we focused on this, so today we're going to be focusing on this one. So let's do that. So this was our Lagrangian, right? So this is what we achieved up here, and we're just replacing the i's where necessary. And we realize that I is different than 0, right? So this term is going to go to 0 because the Kronecker delta goes to 0 whenever the two indices are different. And we get this. So how do we get from here to here? Well, this was 0. The Lagrangian is right here. Okay, this stays the same, and then this stays the same out here. And then we see, okay, well, this guy stays the same here. This guy really just reduces down to one of these because that's again just chain rule. Okay, so we get this. This here we said was defined by this, right? And so our momentum, right? So our momentum is given by this equation right here. That's pretty easy, I think, to understand once we understand this derivation, right? And we have this momentum given by the solution of the Klein-Gordon Lagrangian and its conjugate momentum. All right. So keeping that in mind, we also want to keep these two guys in mind. This was the solution, this was the conjugate momentum, and now we want to plug those in, right? So the book itself, again, this was the book. The book itself covers this in an appendix in the back, and it's long. It's a pretty long derivation, and I don't want to bore you guys with this derivation because I know when some of you guys see that timestamp of, if that timestamp said 40 minutes, you're probably going to want to skip over this. So I'm just going to say this is a long derivation, but it is possible, and once you get through that derivation, you get to this solution here. Now, what I want to do here is briefly talk about what the difference is between this guy and this guy, right? So we achieved this guy in an earlier video, right? This was the Hamiltonian for the system. This here is the sort of the spatial part of that Hamiltonian for the system, okay? Keep in mind, these are all operators, right? They have these operators in here, and that's actually important to understand for what's going to come in the next video. But we want to see that the eigenvalues here, right? So these are operators, constant, constants, integrals, and constants, and there should be over a volume here. We want to see that most everything stays the same, right? We have this here. This is the Poisson bracket between these two things, which is really just the addition of them swapped, right? If we remember that this here is A dagger, A plus A dagger, that's the Poisson bracket. But the only real difference that we see here again is that our eigenvalues are different, right? So we have the eigenvalue for our momentum being our momentum for the spatial part of our momentum, and then this is the temporal part, right? So these are eigenvalues for these operators, right? What does that tell us? Well, that gives us an understanding that, well, if we were to apply this, Hamiltonian operator to this kind of state, we get the same kind of state back with the eigenvalue, okay? Similarly, we do the same thing here. What do these states represent? Well, this is one particle at state with a momentum k, right? So everything has to match up. So if we are looking at, if we want to zero in on a particular momentum, okay, and then we ask ourselves how many particles have that momentum, okay, and we're integrating that over some volume. So within some volume, how many particles have a particular volume or have a particular momentum within that volume? That's what these operators are giving us, okay? If we want to add particles within that volume of different momentum, then we use these commutation relationships, right? So this here is an operator, right? That you could think of these two things as operators in some sense. You know what? I will actually do that. Right? Like, this is very unconventional, but this hopefully will get to the point that this commutation relationship is actually an operator, and that operator is given by these guys right here. Right, so when we apply this guy, or this guy here, to a state, right? So H bar A dagger of K, this is just an example applied to 1K. Well, that's going to be omega K A dagger of K 1K, and so that's going to be omega K times 2 particles with momentum K in that volume. Right, so this is an example of how this works. And another thing we also want to note is that one particle with momentum K is the same thing, like we just said in this example, it's the same thing as operating on a zero state, 0 particles with momentum K. So I will specify momentum K. So one particle with momentum K is the same thing as operating on 0 particles with momentum K using this creation operator. We've created a particle with this operator. Okay, so all of this is to say that we are pretty much almost done with looking at the Klein-Gordon equation. We've looked at the dynamics, we've looked at the eigenvalues associated with Hamiltonians given within some volumes, we've looked at the spatial Hamiltonians. We can investigate the properties of all of these, right? I could, right, do this for, I could keep on going on and on and on with investigating the Klein-Gordon equation, and we're gonna do maybe 2 or 3 more videos before we dive into the Dirac equation. But something to keep in mind is that something we talked about a while ago is that when we talked about the Dirac equation, we noted that there's a very special link between the Dirac equation and the Klein-Gordon equation, namely that this operator here also behaves like a harmonic oscillator, which is described by our Klein-Gordon equation. Right? This is something that we want to keep in mind later when we start talking about the Dirac equation, right? Because a lot of what we're talking about now is also applicable to the Dirac equation, given that we know this, right? So it's not like one Lagrangian for our scalar field is completely different or completely separated from our Lagrangian for our Dirac field. It's not like these are two completely independently separated fields. It's not like one behaves much differently than the other. One behaves similarly to the other when we understand this fact, okay? And that is something we want to keep in mind going forward when we start talking about the Klein-Gordon, or when we start talking about the Dirac equation. And we also noted that the Procca equation also behaves in this way, right? So we're going to discuss the Dirac equation. We're also going to discuss the Procca equation. We're just going to see what the differences are, not what the similarities are between those and the Klein-Gordon equation, because the Klein-Gordon equation is sort of the catch-all term, right? The Klein-Gordon equation describes harmonic oscillating behavior, whereas the Dirac and the Procca equations describe a little bit more nuanced aspects of that very similar like behavior, of that harmonic oscillating behavior. With that being said, I will stop it here. And again, if you like this kind of content, please hit that subscribe button, like, and throw some comments in the videos if that is something you wish to do as well. So I'll see you guys in the next one. Bye.